Okay. So, on the as for the midterm, which I'm sure is a topic of greatest interest. So, as you saw in the email, practice exam and solution posted on lectures page under the October 22nd entry, which is 1 week from today, is the date of the test. This Thursday, October 17th, review. I will be down there teaching and having myself videoed up here. One thing that we'll definitely have time to do on Thursday is going over a practice test. And of course, any other questions related to the midterm we can address at that time. But be sure to look at those problems before then if you haven't already, and also the solution, and bring your questions. Okay. Now, as far as grading is concerned, so homework 3 I did over weekend. All right, so I will try to have the next few days homework 4 graded as well. For the minority of you who have actually turned it in, I think we're up to about half a class has turned that in. So whatever else filters straggles in, I'll take care of those also. Yes. Yours was on paper, right? It has been graded. It is in my office. Well, hold on. Okay. Okay. One second. I'm sorry. Someone else turned it on paper, and that has been graded. But okay. Okay. Let me talk about that. Has been graded. Now, what I've done differently from homework 2, because in homework 2, yeah, you emailed me the assignment, and I replied to the email to give your comments. I did not do that this time, but there are comments posted in Canvas. So I've entered the grade in the Canvas gradebook, and when I do that, it lets me post a comment in the Canvas gradebook with the grade. So you should be able to see it there. Now, posted comments on the explorations are posted there. So including same thing that I would send in the email, because it was just a whole lot easier to just go in Canvas, boom, 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 instead of like starting the email. So are you able to see it? Or what? Have you gone there to look? It's not there? I definitely put it there.
The grade?
The grade and...
I haven't gotten my grade either. I put mine though, I scanned papers in and then I posted those papers for the quiz.
Well, I got your email also.
I sent the email that had the explorations.
Right.
But then I also on campus, like the questions that we do in the back of the book.
Yeah.
I had them on paper, so I scanned the papers and put them on campus in that.
Yeah, I remember that.
Okay. Because I haven't gotten
on Canvas either? Hold on a second. Okay. I'm about to look at something that not everybody should see because it concerns students' grades, so I'm going to temporarily disconnect. Okay. Now, back to the notes. Okay. So I will have whatever homework 4s have been submitted, and And then also, if anything late has come in on previous assignments, 2, 3, 4, I'll get those done also. I will post answers for relevant concept checks. So for instance, I have the answers for the chapter 2. So that's homeworks 2 and 3 concept checks. Those have been previously typed up. So I'll post those somewhere. I'll let you know. And then I don't have solutions pre-written up for chapter 7 concept checks, but that won't take long. So I'll try to get that soon. I will try to have all of this done by Friday, because I have absolutely a blank schedule on Friday that will give me time to do all these things. Okay, so that'll still give you some time to use that info prior to the actual test. Yeah. Is there a question from down there?
Oh, I thought it was Thursday.
What?
Oh. Never mind. I thought this was Thursday. I was studying on.
Oh, no, the review is Thursday. And then.
Oh my God. So messed up.
Okay. All right.
I was stressing myself.
Okay. You have 1 week until Doomsday. So.
I'll probably forget everything by then.
Okay. All right. Does anyone have any questions related to the midterm? Yes.
It's on Tuesday, right?
Yes. Okay.
That was a good one.
Here it has been. Here. Since the beginning of a semester. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right, so there's still about 8 people in the class who are not here, so hopefully they're also aware. But so I expect perfect attendance on that day for a change. We'll see what happens. Okay. Any other questions about the midterm other than when it is? That's going to cover the essential things, but yes.
Yeah, just a stupid question again, but does that also include MATLAB coding problems?
No. That's why I posted to practice. You will see it has none.
Just making sure again.
Okay. All right. Well, that's good to be sure. So prior to Thursday, I want everyone to have looked at the practice test. Okay. Yeah. Any other questions? Basic or otherwise?
I gone through that practice. You have like a link to, like, say for example, we could find some extra problem that we could work. Say for convergence, you only have like those that's in the book and that's it. What if I want to work? Because the more problem I work, the better I get at the problem.
Okay.
That's it. So if you can like with anything that I can do, even 2 more of each problem, it's better for me.
Okay. Let's see. I might have an answer for you. What I'm looking at right now is the textbook that was used for this class when I was first here.
Yeah.
in general, I'm not a fan of it, but I'm checking because there is a section on error analysis. I don't recall if this has those same kind of problems like on convergence and such, but that's what I'm checking. Oh, dang it. It's scrolling way too fast through here. Okay. Or I might be thinking of a different book. Okay. Oh, algorithms.
You can send us the link like after.
Yeah. Well, the thing is, I don't have a link to this particular book. However, I do know because I've done it before. You can actually find like this. Google Books has a limited preview, as they often do. The entire book can be found. I just found it by Google search. I mean, if you look for any book and you also add to your search PDF, if a book is posted out there somewhere for free, you'll find it. So I can say I found this one, and I believe. Okay, this preview will not show me, but I see that there's a section on algorithms and convergence. Okay, so the thing to look for, I'll type it in the notes. Okay, so
I just need a couple more problems. That's all.
Yeah.
Like 2 problems of each, 2 convergence, 2 Lagrange or something like that. Just because we only do 1 to send to you, that's basically it, you know. So
so these are the authors, Burden and Fairs. Can find whole PDF online. It's out there. Well, there are also many editions of it, so who knows which one you'll find, but any one would be just fine. Okay. Yeah. They're basically, I came up with like 1,000 or so. I think it's literally over 1,000 problems in the book overall. So coming up with those 1,000 kind of wore me out, so, as you can imagine. Okay, so, but I think the kind of problems you're looking for you can find in here.
alright.
At least you're not buying a book, which I believe costs well over $300. Okay. Now, other midterm questions of any kind. Okay. Now this last topic, this itself is not going to be on the test, but the thing is, I have to keep the coverage moving along. Although it does relate to things that are on the test, and polynomial interpolation, divided differences. Okay. And then if there's any time left over, we can look at homework questions. Okay. All right. Now, so in polynomial interpolation, we have assumed all along, from the beginning of this chapter, that the x values are distinct. And it better be because, for instance, in Lagrange polynomial, or even in the divide differences, we often had differences of x values in the denominator. So if any of the x values were not distinct, at some point we'd be dividing by 0. So this assumption is absolutely necessary. Now, suppose 2 points of these x values, so xi plus 1, with corresponding y values, yi and yi plus 1, are approaching each other. So it's still distinct. Okay. So I need to zoom out a little bit. Okay. So then what happens is, then we have a following. That the limit as xi plus 1 approaches xi of yi plus 1 minus yi over xi plus 1 minus xi. Okay, so the limit of this quantity, well, what is this converging to? So as the two x values approach each other, this quantity, what is it approaching? As you learned about in Cal 1. Now we assume that y equals f of x. I could write it a little differently, and that might tip you off. So I could write it this way: f of xi plus 1 minus f xi. So what is this converging to? Anyone from Cal 1? Take a guess. I think someone said it? No. Derivative. I think I heard someone say. Okay. All right. I was hoping it wasn't wishful thinking on my part. Yeah. So yi prime, or f of x, f prime of xi, because numerator denominator individually are converging to 0, but when it's 0 over 0, then you have to figure out what the limit is. The limit turns out to be the derivative. So what's happening is these are values from your polynomial also. Your polynomial is agreeing with f at these two distinct points. So what is the result of this is that your polynomial derivative also matches the derivative of f. So far we've only talked about your polynomial matching values of f when the points are distinct. But as points coalesce toward each other, you have the polynomial not only matching f, but the derivative of your polynomial is matching f prime. So this leads to what is called, osculatory interpolation, in which the polynomial, the interpolating polynomial, matches a function and its derivatives at given points. Quick comment on where the name comes from: osculatory interpolation. The Latin word osculare, which means to kiss. So it comes from the convergence of the 2 points to each other, resulting in the matching of the derivative. Okay. All right. Now, so the idea is, so as an example, suppose we want a polynomial that satisfies these conditions at only 2 points, so x naught and x1. So the conditions are, first, we have the same conditions as before, that P of x naught is equal to y naught. So we're given two y values along with two x values. P of x1 is equal to y1. Now, so far, I've not given a degree. Normally I said Pn, but I have no subscript here. That's deliberate. We'll figure out the degree once I've stated all the conditions. Okay. Now, I'm also going to have P prime at x naught is equal to some given value z naught. So whatever derivative of your function is supposed to be, that specifies the value of the derivative of your polynomial. And I'll give one more, say P double prime at x naught is equal to some given value w naught. So I could say that these are equal to f prime at x naught is wait. Dang thing. Okay. And then P double prime is equal to this value w naught, which is defined to be f double prime at x naught. Okay. So all together, we have four conditions. Two on the value of the polynomial itself, and then one on the first derivative at one of the points, and then the second derivative also at one of the points. So in other words, we have three conditions at x naught. This one, this one, this one, and then only one condition at x1. So what degree must P of x have to satisfy this many conditions? Because we only have 2 points, x0, x1. You might think, oh, we can have a line pass through those 2 points, which will satisfy these 2 conditions, but not these. So to satisfy all 4 conditions, what degree does the polynomial need to have? 3. So it must be cubic, or at least cubic, so degree is still 1 less than number of conditions. So that part has not changed from polynomial interpolation we've seen before. However many conditions you impose on your points, whether they relate to the y value or derivative values, doesn't matter. That's how many coefficients your polynomial has, and therefore your degree must be 1 less than that. Okay. All right. So, okay. So now we can have. So if I wanted to come up with this polynomial in the most straightforward way, using power form, I would have okay. So power form would be we'll call P3 of x. Wait, something's wrong here. Okay. Okay. P3 of x equals a naught plus a1x plus a2x squared plus a3x cubed. Okay. Sorry, something is really wrong here in LaTeX. I'm not sure what it is. Okay. Okay, I'll have to deal with that later. So, what we have is, if I plug in the 2 points that I have, so A naught plus a1 x naught plus a2 x naught squared plus a3 x naught cubed, that must equal y naught. So that's the first condition. Second condition, same thing, but x1. So I'm just plugging in each x value into this polynomial, y1. But now, what I deal with is the derivative of this. So that's going to be a1 plus 2a2 x naught plus 3a3 x naught squared. And that has to equal z naught. So this value here, which is the derivative. And then I have one more condition on the second derivative. So I take a derivative of this, and I'll get 2a2 plus 6a3 x naught equals w naught. So now I again have a system of 4 linear equations and 4 unknowns. It's not a van der Waals matrix, although the first 2 rows are like that. So I could go ahead and solve this, but we run into the same problems that we have when solving systems of this type. That it could be ill-conditioned. Also, we have a large number of points. The solution process could be very expensive because for a degree n polynomial, you're performing order n cubed operations to solve this system. Okay. So we like to fall back on methods that more efficient methods that we've seen for a case of distinct points. We had Lagrange interpolation. We also had Newton interpolation. Now, it turns out that using a more Lagrange type approach is extremely cumbersome. We have different polynomials that are like Lagrange, but a lot nastier, more of them. It turns out that using divide differences is a lot easier to adapt. And I will talk more about divide differences in a moment. And I'll step through an example a little later. But here's the idea behind using divided differences. For osculatory interpolation in general, so here's what you do in words, and then you'll see it a little later. Okay, first, if k conditions are imposed at a point, so for example, y value, y prime value, y double prime value, etc., then that point, and by point I'm referring to, dang it, stop that. At one of the x values, then, so that point, xi, no, I don't want those kind of dollar signs. Stop that. Xi has to be listed k times in the divide difference table. All right, so you're actually going to have duplicates among the x values and y values in your divided difference table. Now, once those are listed accordingly, then you go through the same divide difference process with this exception. When computing a divided difference, where you have something of this type, so I have fxi minus fxj over xi minus xj. Now, most of the time you'll just compute this as is, like before. But suppose these x values are equal. then fill in f prime of xj instead, which makes sense because as xi approaches xj, this expression converges to f prime of xj anyway. So it makes sense that that's what you fill in that spot in a divided difference table. So you're avoiding dividing by 0 by filling in the limit as these differences approach 0. Okay. Now, one more point to make is for a higher order divided difference of this form, okay, where I have xi minus xj in the denominator. So I have f, oh, sorry, I went on to a new page. So you have some higher order divided difference here, where I have xi, I plus 1, xi plus 2, etc. Dang thing. Sorry, this editor is really loading to piss me off. Okay. Let me fix my LaTeX code here. X j minus 1. Okay, so it's all the x values starting from xi, going up to xj, but not including it. And then in the other divided difference, we start at xi plus 1, all the way up to xj. So this is a typical higher order divided difference. If xi equals xj. So again, we're in the same situation where we're in danger of dividing by 0. Then we fill in, so for a kth order divided difference, what you do is you fill in the kth derivative at xj, but here's the kicker, over j factorial. Do not forget the factorial. That's very important. And for first order divided differences, 1 factorial is 1, so it doesn't matter. But for higher order divided differences, if this is a kth order divided difference, it's a kth derivative, but you must remember to divide by the factorial. Okay. Now, so I will do an example, but for a particular kind of osculatory interpolation, that's called Hermite interpolation. People mistakenly pronounce it Hermite. It's Hermite interpolation, in which for every x value, x0, x1, all the way up to xn, both the y value and y prime value are specified. So you have n plus 1 x values, and those are distinct. But for each one of these x values, you have 2 conditions imposed. So you have a total of So I have a total of 2 times n plus 1 conditions. So that'd be 2n plus 2. Just because you have n plus 1 distinct points, but 2 conditions are imposed on each. So the degree of the Hermite interpolating polynomial is going to be 1 less than that. Two n plus 1. So before Lagrange interpolation, we had n plus 1 points, n plus 1 conditions, so it's degree n. Now we have 2 times n plus 1 points, 2n plus 2 conditions, so degree 2n plus 1. Okay. Now, so I should mention that the error in Hermite interpolation, so that'd be, so I'm going to use f of x minus, so I'm going to use a capital H to refer to the Hermite polynomial of degree 2n plus 1. So that is going to be very similar to the error we saw in the Lagrange interpolation. So we have, okay, so we have, bless you, whatever degree you have here, you have one more than that derivative. So the 2n plus 2 derivative of f over 2n plus 2 factorial, and then you have these factors, x minus x naught squared, x minus x1 squared, and so on, all the way up to x minus xn squared. Okay. What? Ah, dang it. Okay. Oh, I see what happened. Okay. Yeah, the VGA cable came loose. Let me screw that in a little bit so it doesn't happen again. Okay. So I want to compare this to the formula that was covered last time for the error in Lagrange interpolation, where we only impose conditions on the y values. So fx minus p n of x. So there we have the n plus first derivative, and then n plus 1 factorial. And then these factors are the same except not squared. Okay. All right. So this goes with the idea that in Hermite interpolation, because each point has 2 conditions imposed on it, each point is effectively included in the interpolation twice. That's what leads to all of these being squared. That's what leads to a higher degree. And therefore, the degree of these derivatives in the order factorial are twice as much. Again, from each point being listed twice. Okay. Now, how do we actually go about computing divided differences for Hermite interpolation? Okay. All right, so I'm going to step through an example here. Okay. So here's our given data. We have x naught is 0, x1 equals 1. Okay, check my notes here. Okay. And then for y values and y prime values, we have f x naught is going to be 0. F prime at x naught is going to equal 1. And then I have f of x1 is also 0. F prime at x1 is also 1. So in fact, one function that actually satisfies these conditions would be f of x is sine 2 pi x. Well, oh wait, actually I have to scale it for a derivative. So, f of x could be sine 2 pi x over 2 pi. Because if I plug in x equals 0 and x equals 1 in here, I will get 0. If I take the derivative, that's going to be cosine 2 pi x times 2 pi, which cancels with the 2 pi. And if I plug in x equals 0, x equals 1 into the derivative, I will actually get 1. So that could be a function that's fit. Okay. Now, because each x value has 2 conditions imposed on it, effectively I'm performing interpolation with 4 points. So, 4 points listed in the table, and cubic polynomial. Okay. Now, what I'll do is I'm going to use z values, z0, z1, z2, z3, where these are not necessarily distinct. So z0 will be 0, z1 will also be 0, z2 will be 1, and z3 will be 1. So the actual table now I'll do this as a matrix. Alright, so I'm going to have 1, 2, 3, 4, 5, actually, no, 6 columns. Okay, 1, 2, 3, 4, 5, 6. Okay, so I'm going to have, and 1, 2, 3, 4, 5, 6, 7 rows. Okay, so in my headings, indicate what goes into each column. So the first column will have just my index of my z values, and I'll have zi, and then f of zi, and then I'll have first order divide differences. Okay, and then I have let's see, second order. Oh, something went wrong there. Okay. And then the last column will have my one and only third order. Sorry, I need to put my line breaks in here, so it'll stop squawking at me. Okay. All right. So then I have f, okay, z0, z1, z2, z3. So the last column is a third order divide difference that will have all the points listed. That's why I don't have I in here. It really wasn't necessary. Okay. Okay. Now, what I'll do is I'll fill in my indices and the x values that go with them. So, okay, so those are my indices 0, 1, 2, 3. And then the x values are now labeled as z values just for the indexing. We'll go in between. So I have 0 listed twice, and I have 1 listed twice. Next, I'll have the function values listed here. Now, in all cases, f of x naught is 0, f of x1 is 0. So I'm going to have all 0 values in this column. Okay, so I have 0. Okay, 0, 0, and 0. Okay. Now, I'm going to compute divided differences. So normally we have differences of these values divided by differences of these values. So here I have f of this, so y minus y divided by x minus x, but that's 0 over 0. So this is that situation I was talking about earlier, where for this I fill in the derivative value right here at x equals 0. And that's given right here. F prime of x naught is equal to 1. So that is what goes in this spot in the table. So column 1, 2, 3, 4. Okay, so this f prime value of 1 goes here. Here too, between these 2 points, at x equals 1, so y minus y divided by x minus x, that's a derivative when it's the same point. That derivative value is also 1, so that'll be filled in down here. 1, 2, 3, 4. Okay. Whereas in between, here the x values are distinct. That's an ordinary divided difference. So it's this minus this divided by 1. But that's just going to be 0, so I'll fill in that. 1, 2, 3, 4. So now my first order divided differences are filled in. So whenever the x values matched, you fill in a derivative. Where the x values do not match, you don't have a divide by 0 concern, so you compute the divided difference normally. So questions up to this point? Now, from this point on, we will not have to worry about dividing by 0. If we did, that would come from one of these points being listed more than twice. We'd have to use higher derivatives. But we only have data for first derivatives here. So now I could do 0 minus 1 divided by 1 minus 0. So that's going to be minus 1. So that'll be filled in there. Here also 1 minus 0 divided by 1 minus 0. So that's going to be 1. Okay. 2, 0, 6. Okay. And then finally, I have another conventional divided difference to go in this spot. So 1 minus a minus 1. So 2 divided by 1 minus 0. So that's going to be 2. So then the divided difference table is complete. So to get from this, here we have every y value listed twice, along with every x value listed twice. So every other entry, you fill in a derivative value. All right. Now, once the divided difference table is complete, we need the actual polynomial. And as before, use the top row of divided differences. So I have 0, 1, minus 1, and 2. But watch closely. All right, so in this example, it's a cubic. So I start with this 0, that's a constant term. I'll fill in explicitly. And then we go to the next term, and that'll be 1 times x minus z naught. Okay. And then we go to the next term, minus 1 times, and we remember use these to figure out your centers of your linear factors. So x minus z naught, and then x minus z1. And then finally to the last term, so 2 times linear factors with these free values as centers. So x minus z naught, x minus z1, x minus z2. Okay. But now you take into account what these values actually are. So if I simplify to a point, so that's going to be x minus 0 plus minus 1 times x minus 0. And this value is also 0. So z naught and z1 are the same. So I get x minus 0 squared, and then 2x minus 0 squared times x minus 1, because that's what z2 is. Okay. And then the polynomial can be simplified from there. I want to focus on this because this is what we see in a general case, that you have linear factors, x minus some x value, and you go 2 at a time. So notice we have x minus the first point listed twice, so it ends up being squared. Then x minus 1 appears once, and here we stop because it's cubic. But if I continued, I'd have x minus 1 squared. So just like in Newton interpolation we saw earlier with the divide difference table, as you go through the coefficients, you're tacking on linear factors, x minus this times x minus this times x minus this. That part doesn't change. It's just that because these points are listed twice in a row every time, you get these linear factors squared in here. So really, once you keep in mind that for Hermite interpolation you list every x value twice, you follow, with that condition up front, the procedure for constructing an Hermite polynomial versus the ordinary polynomial for distinct x values, the procedure is no different. I want to emphasize that. Aside from that setup, it is no different except for having to fill in first derivative values in this column, where your first order divided differences. But otherwise, the algorithm you follow is exactly the same. All right, so questions about how this interpolating polynomial was obtained.
Not bad.
Okay, and that's that same polynomial simplified to a certain degree. Okay. Now there will not be a question about Hermite interpolation on the midterm. You can expect one on the final, though. Something along these lines. So when we get to the end of the semester, there will be a practice final, and you'll see it there. Okay. We have some time. Are there any homework questions? On any assignment whatsoever. Okay.
The concept check for 7.3.
For 7 point what?
3.4.
Okay.
Concept check. You said we could find the answers to the concept check in the text that we read.
I wouldn't say that's true for absolutely every single one, but
Yes.
or it's not much of a leap from what's in the book. But hold on. So 7.3,
0.4.
7.4.
7.3.4. That's section 7.3.
and number 4 in a.
Yeah. Oh, sorry, number 30. Describe the relationship between divided differences and higher.
Well, yeah, there's a theorem right there.
Your theorem.
Yes. There's a theorem that states exactly the relationship.
Well, we're not proving the theorem.
What? Oh.
We're not proving the theorem.
No. It's basically this. You're stating the
So
theorem.
we're just stating it.
Yeah. And was there another one?
Um, 7.4.
Okay.
Not the concept check, exploration. 7.4.2.
Oh, this one?
Yes.
Okay.
So how do we bound the error? Because in the example you worked in the book, you use the critical points.
Right. So, yes, it's the same idea here, where so what you'll have in your error formula, because there are 3 points, you're going to have. Okay, so you'll have the derivative. Okay, so in this case, since it's second degree, it'll be the third derivative of f, so of the exponential over 3 factorial. So,
I was talking about the sentence x minus x naught.
yeah. So yeah.
How do we bound that?
Well, in this case, since you're given the x values, you'd multiply that out, and then go ahead and follow the usual procedure for finding the maximum. So yeah, you again, we'll find the critical points.
But the critical point is not simplified to a rational expression.
Okay.
The critical points for this case would be degree 2 polynomial.
Yeah. Well, so in that case, all you can do is, you can give an estimate from your calculator. Yeah. I'm not looking for some elegant expression here. Yeah. Just something to a few decimal places is fine. Yeah. Besides, I'm saying determine a bound. So round up and you get yourself a bound. Other questions? Oh. Okay, so the system of equations, okay, so it still comes from this, but it's from a polynomial written in this form, as opposed to power form that leads to a van der Waals matrix. So in this case, what you'll do is, to get this system, you'll plug in x equals x naught for one equation, x equals x1 for the other equation. Yes, which is actually the nice thing about this. Hold on, please. Let me answer this question. So that's the nice thing about that system, is that each equation has only one unknown in it, so you can solve them independently of each other. As opposed to what you get from this system, where everything's coupled, you got to do elimination and substitution and all that. But now, in this system, you don't have to. So the idea is, how do you achieve a similar outcome for the second degree case, where you have a polynomial in a form somewhat like this, but quadratic, where again, each equation will feature only one of the three unknowns, A0, A1, or A2. Um, well,
Well, if the goal is to get it in terms of one unknown,
yeah.
so
Uh,
don't we need Vandermonde matrices?
Right, we don't. Because Vandermonde matrices are tied to one way of expressing the polynomial. But if we express it a different way, we have a simpler system. So the idea is, like here we had, instead of using just polynomials 1 and x, we use x minus x1, x minus x naught. So what quadratic polynomials should we use to have the same thing where if we plug in x naught, x1, x2, that most of the terms will disappear? And that's what leads to Lagrange polynomials. So you have the luxury of actually being able to peek ahead at that, even though it's in the section after this one. But we've covered it. Other questions? There's something down there? Any questions at all?
7.3.8.
7.3.8?
Yeah.
Okay. Okay.
Okay. So it says the vector XX.
Mhm.
In the algorithm we're using, that XX is standing for the X in the algorithm, right?
Yeah. So each element of XX would play a role of X in here.
So are we looking for a specific value? Because when I did this, I tried testing using the method you posted on the website.
Oh, right.
Well, it said something about the problem with this part of the code. That's BI. That the left hand side does not match the right hand side. So assignment is not.
Oh. Okay. And that came up from trying to run your function or from trying to.
I'm trying to test it using.
Yeah.
I tried to use the example. One of the problems that was solved here as the test data.
Okay. And it said that. All right. So that kind of error comes up from doing something like trying to assign like something that's a vector quantity to where the left-hand side expression refers to a number, some sort of mismatch like that. So the way this ought to work is when you're using this algorithm, you're using it with one element of XX, and then the result here, once this concludes, will be one element of YY. So that way, everything you're dealing with in here is just a number. And so that's one way you would avoid that particular error. But that means you have to refer to, you have to use subscripts or indices to refer to everything. So XX parentheses, like XX parentheses J up here, YY parentheses J down here.
So what if you are we going to create another loop for the J?
Yes, you would need an outer loop surrounding this to go through all of those elements of XX. If you continue to have that kind of problem, then I can look at your code and see what the deal is. And then, well, that goes for everybody. Any other questions in the last 17 minutes we have? Yep.
Say we're looking at the last three is 7.4, 3, 4, and 5, where you give the cosine formula.
Yep.
So we should just prove one proof will cover all then.
So for this one in particular, I mean, you're proving three separate things, so I'm not sure what you're asking.
So we should prove all three of them
I mean, these?
separate.
Okay, so, yeah, first you're proving this, 720. And then these three will help you. You don't have to prove these. I'm not sure if that's what you're asking. But you can just go ahead and use these. Yeah, so in this problem, 743, only this, only that you are proving. And yeah, then the next problem, this will be used to prove its fact about the leading coefficient.
Yeah, like K equal 1. Okay.
For proactively giving a tip about this one, so as far as like showing that they are, real, distinct, and lie within a certain interval, so that boils down to the behavior of cosine, really, like showing they're distinct. Now, because all of the roots of a Chebyshev polynomial were given by this formula right here. So you're trying to show that these are real, distinct, and lie within -1 to 1. So now cosine is not what they call a 1-to-1 function when it's considered on its entire domain. However, cosine is 1-to-1 on, like if you choose the right interval. So for example, on the interval from 0 to pi, cosine is 1-to-1. So you can use that to show that the roots. So what I mean by 1-to-1 is if you plug in different x's, you're going to get different y's. So that's something you can use. Okay, I'll add that to the notes here. Whoops, really bad spelling there. Okay. So on 7.4.5, use the fact that cosine x is 1-to-1 on the interval 0 to pi, which means that, okay, those of you who've taken modern algebra, that means same as meaning it's injective. So if x1 is not equal to x2, then cosine of x1 is not equal to cosine of x2. All right, so that helps with the part of showing they're distinct. And that's important because polynomial interpolation, we're assuming EX values are distinct. Well, we needed that until today anyway. So it's important that Chebyshev points are known to be distinct. And for another part of the same problem, notice I have the open interval here, -1 to 1. So -1 and 1 themselves are not to be included. So keep in mind, where is cosine equal to plus or minus 1? Which angles? So if you can show that the these angles where it's cosine is equal to plus or minus 1 are not among the ones plugged into a formula for cosine for a formula for roots, then you know that this holds. All right. Okay.
Here.
All right.
Cosine's inverse 1.
Okay.
Cosine.
Yeah, because your arc cosine or inverse cosine, it has a domain of minus 1 to 1 inclusive, and its range is defined to be 0 to pi. So limited to that domain, restricted to that domain, it has an inverse. Okay. Any other questions? All right, well, keep the homeworks coming and I will grade them. Okay.
I'm still not getting the relationship between the Lagrange.
Oh, hold on a second.